Okay, so for topic 12, first let's talk about the photoelectric effect. Einstein did these experiments where he shone some light on some metals that are photosensitive. In other words, the light hit the metal and electrons were released from the surface of the metal. And so the setup basically looks as you see in the diagram. But first, before this happened, let me just, when I talk about the collection plate. The collection plate is this guy, collection, that side. That's the collection plate. And then the emission plate is the other side. But before, you could see that from the picture that the emission plate is the negative side and the collection plate is the positive side, which makes sense if electrons are the things that are being released and collected on the collection plate. But first, before they did that, they actually connected the collection plate to the negative terminal, which doesn't seems not to make sense because if it's electrons that are being transmitted from the emission plate to the collection plate and the collection plate is negative, then those electrons are going to be repelled by the collection plate. So that collection plate is repelling the electrons unless those electrons have enough energy to overcome that repulsion. So we know, of course, that potential difference is energy per unit charge. And so the energy of the electron is the voltage that it's fighting against times the amount of charge on the electron. And so if the electron had enough energy, enough of the energy to beat the voltage, like if the energy of the electron, if that W were greater than VQ, then those electrons could be collected on that collection plate despite the opposing voltage there. However, what they did in the experiment is that they increased that negative voltage, and they basically reached a point where that negative voltage was so strong that there was no energy available to the electron. The electron energy had a maximum value, what they call the maximum kinetic energy, or Emax. That maximum kinetic energy was the maximum energy per electron to overcome VQ. Eventually, they increased the voltage until no electron could hit the collection plate, and that was the point. They call that basically the maximum energy, like the top out energy for the most energetic electrons that could hit the plate. That was the maximum energy, and eventually you hit a voltage where no electrons can hit, and they call that the stopping voltage. Now, the reason why I bring this up is because this review sheet makes reference to maximum kinetic energy, but there's a backstory there on maximum kinetic energy that I wanted to explain. So yeah, the maximum kinetic energy on those electrons is the most energy for each electron to overcome that stopping voltage. But then having a negative voltage on the collection plate makes no sense, and so they flipped it back around. They connected the collection plate to the positive voltage, and so, of course, many more electrons would go to that positive collection plate. All right, so I'm going to erase what I wrote, but I did add on the top left there about Emax, because we're going to be making reference back to Emax in a minute. All right, so like I said, they set up the photoelectric effect experiment as shown with the collection plate on the positive terminal of the battery, and so more electrons, of course, transferred across because they were repelled from the negative plate, the emission plate, and they were attracted to the positive plate. But what happened was that the positive plate started to get, as you increase the positive voltage, it really started to get saturated with electrons, that every single emitted electron was collected onto that plate, and then there was an upper limit on the amount of current that you could actually produce given a fixed intensity beam. And so here's actually what happened. I'm going to use this space over here to show what current we wind up getting versus the voltage across the plates. So yeah, the actual current curve, it increased up to a maximum current, and but this curve goes back into the negative voltage. Like I said, if you start increasing voltage in the negative direction, you eventually hit a negative voltage over here where the current is zero, and that is the stopping voltage I made reference to earlier. And you might be wondering and say, well, okay, that's fine. That's when the current is zero. That's the stopping voltage. But what about when the voltage is zero? When there's no voltage across the plates, you're still going to get a current because of the effect of the light bumping the electrons off of the photosensitive material. So even when there's no applied voltage across the two plates, there's still going to be a voltage pretty much created by the light on the photosensitive material. So that's why even when voltage is zero, there's still a current there. Now I'm looking at the SOCOS text. We're talking about nanoamps here in terms of current, with voltage in positive single digit volts. So we're not talking like truckloads of current here. But one of the big deal things about the photoelectric effect was that even though physicists had been working with light operating with wave properties such as interference and diffraction and things like that, the modern physicists such as Einstein and Max Planck figured out that light also has properties of a particle. And an example of that is the photoelectric effect in solar photovoltaics. But in topic 12, we actually get into how did they actually discover that. And so we know that light does operate like a wave. It's not that light does not operate like a wave. We have examples of light acting like a wave in which acting like a particle would make no sense, like interference and diffraction of light waves. But then physicists were like, okay, light acts like a wave and it only acts like a wave. But what Einstein and Planck discovered was that light also acts like a particle. And so what it's saying here is that if light was a wave, like in terms of this experiment, if light were a wave, a more intense light beam would cause more electrons, would cause there to be more of a, I should say the energy of the electrons should increase, as because and the intensity of light is related to the energy per unit area. So if the intensity increased, then the energy of the electron should increase, and that was not the case. So that's the first point there. Increasing the intensity would increase the energy of the light and would eventually the electron would have enough energy to be removed from the metal, and that actually did not happen. In fact, what you might think, going back to our notion of the maximum kinetic energy, that if you increase the intensity of the light, in the SOCOS text they use the example of a candle or of a spotlight or a searchlight. If you increase the intensity of the light, you should be able to deliver enough energy by the wave model that the electrons should be able to push against that repelling voltage, and you should be able to get past the stopping voltage. And what they found is that the intensity did not matter at all. So yeah, there was no effect on that maximum kinetic energy, which is completely opposite to what we know of wave theory. We know that that intensity is related to the square of the amplitude of a wave, and that a more intense wave should have more energy and should have delivered more energy to those electrons. That did not happen. So that's one way in which the wave theory was broken. Another way the wave theory was broken is that there apparently was it was called the threshold frequency. So as Einstein changed not the intensity of the light, but the frequency of the light, he found that there was a minimum frequency where no electrons were emitted from the photosensitive surface at all. And the threshold frequency was the minimum frequency where you could bump electrons off that photosensitive surface. I mean, that's what it says right here. Threshold frequency is the minimum frequency that would release electron from the surface of a metal. Any less and nothing would happen. And by the wave model, I mean frequency is not related to the energy of a wave. It's related to the energy of a light wave, but that's for a different reason, which we'll get into in a minute. But I'm talking about like the frequency of, say, like a water wave or a sound wave that has no relation to the energy of the wave. So it's not like all of a sudden, a frequency drops and now suddenly there's not enough energy to bump the electron off the photosensitive surface. That makes no sense when it comes to the wave theory of light. So that's another thing that doesn't make sense with wave theory. So wave theory is really getting beat up here. Okay, well, let's go back to this notion of a photon. And so Max Planck and Einstein theorized that, all right, so wave, these experiments are breaking down wave theory, which is a good thing when you do an experiment. You know, if you find new information that goes against, you know, your hypothesis, then that generates new questions to investigate. Now, Max Planck was actually working with black body radiators, things that are giving off light based on their temperature, and there was something called the ultraviolet catastrophe, which I think is fantastic. The ultraviolet catastrophe. That's ultraviolet, not ultraviolent. That would be much worse, maybe. But yeah, so ultraviolet catastrophe, looking at Wien's law of radiation, and what Planck found was that the curves expected for wave theory down at the ultraviolet range, you know, totally did not match what was observed in terms of actual black body radiators. So that was another problem with wave theory. So both Planck and Einstein were bumping up against problems with wave theory, and so they theorized instead that energy said, what if you treat light instead of as a wave, you treat it as a particle, and as like a packet, and each packet of energy called a photon has energy related to the frequency of that light. And Planck went further, having to do with the ultraviolet catastrophe, saying that not only is energy related to the frequency of its light, but it can't be any continuous value, it has to be discrete values. And so energy is quantized in discrete packets of the frequency of the light times Planck's constant, which is 6.63 times 10 to the negative 34 joule seconds. A good analogy is with money, a currency, the smallest amount of currency that you can have is a penny. So when you think about it, any price, when you say $1, 1.00, that's actually 100 pennies. And so any retail price is quantized in discrete packets of 1 cent. And you can't have anything less than a cent. And so we can't have anything less than a single Planck's constant of 6.63 times 10 to the negative 34 joule seconds. It's also one of the smallest, I think it's the smallest constant in nature, making reference to Planck's constant, Planck's time, and Planck's length. But anyway, that's another ball of wax. And so we have that energy is Planck's constant times the frequency. Now, as the frequency increases, we have more energy, and as frequency decreases, we have less energy, and this would actually explain the threshold frequency for getting an electron off of a photosensitive surface. Which, one other comment before I get back to the threshold frequency, E equals HF is the first formula under subtopic 12.1. So there you go. And then V equals F lambda, so of course we can also write it as E equals hc over lambda, where c is the speed of light in vacuum. Great. This is going to come into play in a second, but I'm going to get back to this notion of the threshold frequency. So yeah, the threshold frequency is the minimum amount of energy in order to bump the electron off the photosensitive surface. But in other words, that would release electron from the surface of the metal. You're trying to give the electron enough energy to get away from the atoms that are holding on to that electron. And so basically frequency is not energy, right? And so we said before that E is equal to HF. And so that minimum energy to release the electron is equal to H times that threshold frequency, the lowest frequency to bump the electron off. Now we actually call that that H Planck's constant times the threshold frequency, we give that a name, and that's right here. I think that's a lowercase phi, I think. Doesn't matter, we call it the work function. And they rewrite that equation as the threshold frequency is the work function over H, which is not on the data table, but the work function does come into play in another equation. So yeah, if we say that the work function, that HF naught, is the minimum amount of energy to bump the electron off the plate, I didn't say the electron, to actually get the electron all the way across the gap from the emission plate to the collection plate. I said just to get it off of the photosensitive surface. So we're going to need more than the work function. That's what it says like right here. This is the energy just to remove the electron, not to move it away from the emission plate. And this is the equation, this is the bush that I'm beating around. This is the actual energy of the light. E equals HF, the energy of the photon. that's the photon energy, is equal to the work function, which is the amount of energy to take that electron and actually bump it up and off of the emission plate, but you still need to cross the gap from one plate to the other. And the kinetic energy to cross the gap is that EK. And so for the reference table, the ref tab reference, we have that the maximum kinetic energy that you're going to get out of an electron coming off of the emission plate is the Planck's constant times the frequency of the light that bumped it off minus the work function. Remembering that, of course, the work function is h times the threshold frequency, aka the critical frequency. So you're going to have to remember that because that part is not in the data booklet. All right, so now that we've established that the energy of a photon is related to its frequency, I'm going to come back to the graph that I drew before about current and voltage and the stopping voltage. So that stopping voltage is related to the frequency of the light. So going back to my point before, that the kinetic energy of the electron is related is the maximum kinetic energy is the maximum electron energy to overcome the stopping voltage. But if you can increase the frequency, then you can increase the maximum kinetic energy. So therefore, higher frequency light has a higher negative stopping voltage. So yeah, as the frequency of the light increases, that maximum kinetic energy of the electron increases, so that stopping voltage, in order to stop that electron, you would require more negative voltage in order to stop that electron. So I drew in curves for, say, like red and blue light. We can also note these relationships with a graph of kinetic energy versus frequency, where again below that critical frequency you're not going to have any energy, and so if we just extrapolate that line down to where the kinetic energy is zero, or rather where the frequency is zero, that amount of energy, this quantity right there, that's the work function that you need to overcome to have any kind of kinetic energy of the electron coming off of the emission plate. So the y-intercept of that graph is the work function, the x-intercept is the critical frequency, or threshold frequency, whatever you want to call it. And I already have the graph. I didn't know this was over here. Let's see, did they say anything that I didn't just say? It says the gradient represents Planck's constant. Oh yeah, the slope, that's important. Slope is Planck's constant, and that y-intercept is the work function. So yeah, I'm sure that's gonna pop up. Slope equals h, and yeah, y-intercept is the work function. Wait, there was one more thing I wanted to tell you, and that relates to de Broglie wavelength of matter. It seems that HESSEL does not include de Broglie, and so I want to go back to E equals HF and comment on it. So yeah, particle physicist Louis de Broglie said that just as, this is where wave-particle duality comes in, by the way, that's kind of a big deal in modern physics. So wave-particle duality is when both light and matter show, that looks like it says matter, show wave and particle behaviors. And so what the photoelectric effect shows is light acting like a particle. Because it can't act like a wave and show the behaviors that it did in the photoelectric effect experiment. But then matter as a particle also has wave properties. That was kind of like the proposal from de Broglie, and de Broglie said that the what's called the wavelength of a particle is Planck's constant over the momentum of that particle. I guess you could say like mv, because they have a mass, of course. And this was actually proven experimentally by the Davison-Gemmer experiment, where they were working with an electron beam, and they accidentally actually shone their electron beam onto a single crystal of nickel. And when they shone that electron beam on a crystal of nickel, that crystal diffracted the electron beam, which would make no sense at all unless, of course, electrons have wave properties, which we now accept to be true. but that is the de Broglie wavelength. Let me write that down. And then I guess technically, every object has a de Broglie wavelength, but only small, very small particles have any kind of appreciable wavelength to them. So you could say that an electron traveling very quickly has a de Broglie wavelength, but a baseball has no appreciable de Broglie wavelength. I think that was the thing maybe in the Matrix where Neo was like dodging bullets because of like the wavelength of the bullet, or I no, not a thing. Not for bullets. Sounds good though. All right, time to move into Bohr. That's Bohr, not bore as in what this video is. Like the rest of my jokes. But yeah, so let's move on to that worksheet. That worksheet is not here, so I'm going to close this video and start a new one. Thanks.